a mouthful of a project. So the first question is, what are these solvers? And these are just the kind of methods that underpin programs like Flaxus that are really trying to work out a materials response to loading. And so the aim of my project has been to look at the ways that's currently being done, to look at the advantages of a few different methods, and then trying to combine them into one hybrid that takes all of the benefits. So what we're going to do this morning is just quickly look at 3 of the ways that that's being done at the moment. I'll point out some pros and cons for you. Then I'll show you a key observation which really underpinned why I was doing the project. Then walk you through how we actually formed this hybrid scheme. So the first of these 3 methods is the initial stiffness scheme. This one really uses the elastic relationship of a material to work out its response to loading. It's a very simple approach. It doesn't take much computation, but it takes a lot of iterations. So you'll see up there in the graph, each estimate, the red diagonal lines are its estimate for the material's response. They're all parallel, which just shows it uses the same stress-strain relationship to finally converge to the solution. So that's why I've called him the eager first-year student. He's pretty simple, he's eager, but he just does the same thing again and again until he finds his answer. The second of the 3 schemes is the Newton-Raphson scheme with what's called a continuum tangent formulation. And he's a bit smarter than the first guy. So you'll see up there the red lines, they aren't parallel anymore. They actually lean over towards the solution where it's trying to get up in that corner. So he learns as he goes. After each estimate, he looks at the way the material is yielding, looks at what's going on, and makes a smarter assumption the next time. So I've called him the savvy graduate engineer. He knows how to make assumptions and cut out a lot of the work in the middle. And the third scheme that's being used at the moment is the same Newton-Raphson, just like the second, but it has a consistent tangent formulation. And that just means the way he works out the stress-strain relationship to use is different to the second one. It takes a bit more work. It uses bigger differential equations, so it's a lot more computationally heavy. But what you see is he really gets to the solution fast. Like he converges really quickly. So I've called him the overpaid consultant because he'll get you straight to the point, but it'll cost you in computational power. Okay. So here's one of the key graphs for my project. It was one that came from work beforehand. What you'll see on the vertical axis is a measure of equilibrium. So within the system, you want to solve it so that there's equilibrium. So when the solution gets down below this line, that's when you've converged to the answer and you've found the right response. And along the bottom is just the number of iterations it takes to get there. And as you look at this graph, there'll be 2 things that you see. The first thing that you see is that they're quite different. So this consistent method, this is the overpaid consultant. He's really quick, he's really smart. He only took 6 iterations to find his solution, which is great. That saves a lot of time in the long run. But the continuum method, the graduate engineer, he's still plotting at about 40 iterations. He's still struggling away. So he's taking time to converge. So that's one thing. These are very different methods. The other thing you'll see about these 2 methods is they're quite similar. For the first 4 iterations, they perform about the same. So the question here is, why would you pay an expensive consultant to do the work which a graduate engineer could do? If they're giving you the same solution for those first 4, why would you use an expensive method when you could use a cheap one? And then hopefully swap over to the expensive one to get the benefits there. So that's what I've been trying to do. I've been trying to think through how do we make a hybrid that really uses this cheap method until the expensive one's actually going to pay off and give you the results. And in doing that, there have been a few questions as into when do we switch? How many iterations do we use this cheap method for before we jump to an expensive one? In this case, you'd say, yeah, it's about 4 iterations. That's when they change their behaviour. However, different problems have different circumstances, so it may be 6, maybe 20, and maybe 1. You really need to know what is it about this method that causes it to converge and find the solution so quickly. So I went on a bit of a goose chase to try and find out what is it about the scheme that makes it work so well. And what we found is it's related to the stability of the problem. So if you imagine Plaxis, you've probably all used Plaxis. You've got the screen in front of you, you've got the soil profile, and in that soil profile it's divided up into a mesh. And on top of the soil, if you put a footing, the load comes down, and right under that footing points stuff. Some will get overstressed and they'll yield. They'll change from elastic to plastic behaviour. And as the load increases, more points will yield. And so you've got kind of this changing system where some points are yielding, some points are not. And what we've found is, once the solution works out how many points are going to end up yielded and how many are going to stay elastic, once that has stabilised and it's found the final, that's when the consistent scheme, the really smart one, converges quickly. So that's shown in this graph. This is some of our results. The red line there is the total number of points yielded, which you see kind of flattens out at the third iteration. And the blue line there is the measure of equilibrium, which is the convergence, which you see at the third iteration. When the red line stabilises, that really increases and finds a solution in 5 iterations. So from that point, after we observed that, and okay, stabilisation is the key, we ran a whole bunch of different problems, trying to gather data from them all to find out when this stability tends to occur, when all these red lines would flatten. And so we found that it's a pretty quick trend. Most of it happens in the first few iterations. And so we found at the 4th iteration, 96% of problems had reached this stability. And so we said it makes sense then to employ a cheaper scheme, the continuum scheme for the first 3, and then when it flattens out, when it stabilises, we'll employ the expensive, but very powerful, consistent method. So that's the hybrid we made, and it seems to have worked well. So here's one of the problems we ran with it afterwards, just to see how it went. As you'll see there, the green is the consistent, that's the overpaid consultant that works really quickly. He found the solution in 3 iterations. The blue line there is the continuum, that's the graduate student who took 12, it's a bit longer. And the purple and the red are 2 of the hybrid schemes that we made, which perform quite differently. The red's pretty interesting, he's up there doing his thing, but let's look at the purple for a second. The purple is the one with 3 of the cheap methods before going to the expensive consistent scheme. And you'll see that he took 4 iterations to find the solution, which is actually 1 more than the pure consistent scheme. But the key is, because we used that cheaper, less computationally intense method for the first 3 iterations, the time that he took to find his solution was only 19 seconds compared to 25 for the green consistent scheme. So even though he took 1 extra iteration to find the solution, he only took 80% of the time, which is the kind of result we were looking for in trying to get all these benefits together. The red guy, I almost had a heart attack when I saw him up there. I was like, what's he doing? What's going on? Why isn't he down where we'd expect him to be? And what we've done there is we've taken this hybrid scheme and we've shifted back the 3 continuum and the consistent. Thank you. And we've put an elastic iteration at the front. And the idea is that with the elastic, we're trying to capture the unloading behaviour of some of the material. You all know that as the material loads, it travels along the elastic kind of region before yielding, going to plastic. But when it unloads, it doesn't come back along the plastic. It comes straight back parallel to its elastic relationship. That's the way it works. So we've tried to put that iteration there just to capture some of the unloading of the problem. And so I looked at that and ran a bit of a sensitivity analysis and worked out how much does this elastic guy affect things. And we found out that obviously he's related to the elastic modulus of the material. If you've got a very stiff soil with a high elastic modulus, then that first iteration is going to throw out your analysis. It's going to take convergence, it's take much longer. But if you've got a less stiff soil, then he doesn't make too much of an impact. But he still captures that unloading, which is important in finding the solution. We also found, just as an aside, for problems where you apply a load, the elastic iteration was pretty cheap and it worked and convergence still came quickly. But for problems where you apply displacement, the elastic again threw out convergence, just because of the nature of the stress strain relationship. Okay, I think we're just about out of time, so I quickly have other solutions to show you. But in the interest of time, yeah, thanks for listening. We found achieved our aims of investigating these schemes and forming a hybrid. Yeah, so are there any questions?
Question?
Hi.
Okay, Claude.
What sort of problems were you testing on? Geotechnical, obviously, but technical?
Yeah, so we used a flexible strip footing for most of the work,
Yeah.
but then we also considered a rigid footing and a biaxial problem, and a whole range of different soil parameters, I guess, in that.
I actually had the same question. So, was it like, were the outcomes sensitive to the type of problem? Or?
No, they were pretty consistent. I guess we just found that the biggest factor would have been whether it was an applied load or an applied displacement.
Yep.
That really affected just with that elastic iteration that before.
So is it sensitive to both? Some problems are slightly nonlinear, the others are highly nonlinear. So does it affect it?
Yeah, well, with problems that are linear, that stabilisation of yield points will occur very soon, and so the consistent method will converge very quickly. So in that case, the hybrid is going to take longer to converge than the consistent method. So yeah, I guess the hybrid, the real benefit is when you do have nonlinear activity.
So have you estimated roughly in a realistic geotechnical problem how much time you can save by using this hybrid scheme?
Like for a bigger problem. I guess it's hard to estimate, so it's going to depend on the nature of the problem. But it's the kind of scheme that you use to underpin an analysis program, which is just going to run hundreds of these things. And so in one case, it saved 20% of the time in that solution. And that's just something that'll, the bigger your problem, the bigger that 20% is going to be. So, yeah, just do this.
Any other questions?
In the biaxial problem, you tested only one element. Was an element test or?
We tested all of the elements inside.
Yeah, this one.
It was just one. This is the final increment of a.
No, I mean your grid was just one element or multiple elements. Your analysis.
Like the finite
The
element.
mess.
Yeah.
The mess.
Okay, it had 800 elements. Yeah.
So, can you explain again why the unbalanced force is higher when you are using the EPC?
The red one, the
Yeah.
elastic. Yeah, the reason is just quickly like that. So the stress strain diagram, unlike that. We've broken up the kind of applied displacement into a bunch of increments and you solve each one. And so, say you're working in this increment up here, when it uses this elastic relationship, it makes its estimate still quite steeply. Whereas the other methods, by this point in the problem, they're using a more tangential approach. So they're, I guess, working like that.
So the first increment it creates a larger unbalanced force.
If you use the first iteration, if you use an elastic kind of relationship, it'll, oh sorry, that should come up to meet this line, so that's our applied. And so obviously the stiffer relationship.
Thank you.